And welcome back. Yes, this week we're going to go through this circuit board here. Yes, this is actually my bin lid monitor, but there are many uses to which such a simple board with a simple trigger could be put to use. After all, what is this? What does it do? I want to do a shout out for JLC PCB. No, stop, don't go away. Look what they're doing. $2 for aluminium circuit boards. This is absolutely incredible. If you've ever wanted to try an aluminium PCB, now's the time to do it. Now remember, aluminium PCB is a single-sided normally with the aluminium on the bottom. Then you have a dielectric layer that transfers the heat up to the top copper layer. Now aluminium is very strong and it will suck the heat away out of your components without the need for extra heat sinks, for example. Go and have a look at their website and check them out. And there's more. JLC PCB now allow you to create your own parts library, because there's nothing more disappointing than creating a PCB and then finding you can't get the parts or there's a big long delay. Now you can create your own custom parts library to ensure you get the components you need, and of course the associated footprints, so you know they're going to fit on the PCB itself. To get to this page that describes everything you ever need to know about creating your parts library, simply go to their homepage and then click on the link at the top. Very simple and a really useful feature. Go and check out JLC PCB now. Basically, it's a remote module powered by a battery that sends out a radio frequency signal to a receiver, in this case this one over here. So what could it be used for apart from bin lid monitoring, right? I guess there's not many people who want it to monitor the bin lids. Sorry? Tell us about the bin lids, Ralph. Oh, all right. My bin lids. Yes, I've got some storage bins out the back of my workshop that go up like that, and I've left them open in the past. It's rained, and everything else inside has been absolutely water sodden. I mean, it's ruined a few things. So what I thought was, it's going to happen again. Bound to. Well, it has happened, in fact. In all honesty, I need something on that bin lid to tell me when it's been raised, so that I can see in my workshop that it has been raised and I ought to be doing something about it rather than just leaving them open forever and a day. Now what else then could this detect? I mean, my tilt switch is there, that little thing there, and I think you might be able to hear it beeping actually. If I lift it up that way, you'll see the LED flash and there it goes, and the beep to say, yeah, I've just transmitted a packet across this huge distance here of about 2 centimeters. But what else could we put in here instead? Well, you might want to know perhaps when your gate is opened, yeah, or when post has been delivered, a little micro switch or something, or perhaps parents want it on a particular door, so they know perhaps if a shed door's been opened or something like that, or even, dare I say it, somebody living at home with their siblings might want to know if their door or something's been opened in their bedroom by one of their siblings when they shouldn't be in there. I don't know. Whatever it is, at the end of the day, it's a trigger. This is a trigger, this little switch, isn't it? And when it's not triggered, it's off, because I've designed it so that it's controlled by a little chip down here, SI4599. Well, all right, I'm lying. It's not an SI4599. It should be. That's what I designed it for. But in fact, I found that my SI4599s were in fact substitutes. By me, yes, it's deliberately done, but they are replacements and they work just fine. Plug-in replacements. So I'm leaving it to your imagination what you could plug in there, but it is actually a hard switch. It's not a how can I put this? It's not a digital signal unless you can bring something down to ground, which you can do, of course, if you, like I think I mentioned this before, something you step on, like a burglar mat. I think some people have those inside their houses, so if the door were to be opened and somebody were to tread on the carpet, it makes a low signal, and that could trigger this quite happily. But let's not concentrate too much about what this does for me. Think about what it could do for you, bits of it. But I thought I'd go through a few steps with you to see how, as a newcomer to the Arduino, not total noob, but somebody who knows a little bit about Arduino stuff, how they'd approach this project. And because it looks now, even to me, it looks like, there's quite a lot going on here. How do you actually get to this sort of stage? And how come this works for me, but I get lots and lots, as you can imagine, questions about, I've done this and I've done that, and this isn't talking to that, and this isn't working, and then that goes wrong, and it's like, everybody makes the same mistake unless you've been trained in how to do this. So let's think about this, okay? First of all, this needed to be battery powered, obviously, because it's sitting out there in the bins, my storage bins out the back. Yes, I probably could have run power out there, you know, from the workshop. After all, we're only talking 2 meters. But that means running a cable out there, and it'd have to be a low voltage cable. I wouldn't really want to run mains cable out there, because then, you know, it could get damaged and all that. So I thought, well, so I'll run a 12 volts, and where am I going to put it? I can't put it under the ground because this workshop sits on a concrete base, and next to the concrete base, there's about, I don't know, 100 millimeters of gravel chippings inside plastic egg crate type things for stability. I think they're called gravel stability plates. So I can't dig down. So I'd have to run the cable over the top. So that was a non-starter. So I thought, no, let's use a battery, because then we can use sleep. Yeah, in the Arduino world, we can get this down to, well, low microamps, maybe less than 100 microamps. And when it's off, actually not being used at all, it should be 0 by virtue of this little thing here, as I said. So I didn't want to have to take this battery out, because taking this battery out, one, it's pretty difficult to get out of this socket, and secondly, the risk is always you're going to put it in backwards. Now you can see I've got minus on here, and I've got plus on the board here, and I've inside here, which I'm not going to take out for reasons I've just said. There's pluses and minuses, because if you put this in the wrong way round, most of this will probably just go up in smoke. All right, there's no two ways about that. So I thought, I don't really want to take this out. So let's add on this TP4051 battery charger. It's an intelligent unit. It's well thought of. It does work in that sense. It will charge the battery up to a certain voltage and then stop and cut off. What it doesn't do, if you can see the USB socket down here, it's not really designed to charge the battery whilst the load is powered. Now that's fine by me, because this is going into this container, which was the container wasn't purpose designed, but the PCB board was to fit inside here, and it's a waterproof container that's going to go inside my bin lid, and I'll just whip this circuit board out from there, plug in a charger one day, it will charge up within, you know, a few hours, a morning let's say, and then it will be done, right? So I don't have to think about it too much. And having done my calculations of all this will last for about 18 centuries, I think it said. All right, let's be more realistic then. With a certain number of bin openings and the time that the bin is going to be opened, during which time this is going to be in sleep mode for most of the time, and then of course the bin lid is shut, the tilt switch moves, the power module here, the dual MOSFET, shuts off, 0 power, 0. Less than, well, it's unmeasurable, I can't measure it on my equipment, so it's less than 0.1 microamp, and I suspect it's probably in the nano amps or pico amps or something. Okay, so it's off. So this is going to last an awful long time. It is, after all, an 18650. Yes, and I know you can buy 18650s and it's got things like 5,000 milliamp hours written all over it, which is nonsense. The highest 18650 I think you can get, capacity wise, is about 3,500, I believe. Now, I did put a link into a website that looks at these in quite some detail. If I can dig it out, I'll add it into the video description. But, you know, an average one like this is a Samsung battery actually. I'm going to call it 2,000 milliamp hours. I think that's a conservative estimate. That will last me for months and months and months. And you have to be careful though. I said this is Samsung because it says Samsung on it somewhere. I can't actually turn it round, but it does. It has got some writing that says Samsung. But there is, of course, the small faction, wherever they exist, they take cheap rubbish batteries, rewrap them in this sort of shrink wrap stuff, and what was cheap, no brand, pretty dangerous rubbish gets sold as a Samsung battery. But I bought this from a very reputable supplier, and you hope they've done their work, background work correctly, and are not buying rubbish and, you know, relabeled stuff. So I'm confident this is what it says it is. So together then, the TP4056 plus the battery is absolutely fine by me. Oh, by the way, Andreas Spiess has got a video on how to modify one of these so that you can add in these 2 points here, those 2 solder points there, that one and that one, a solar power panel, right? It connects it up, and it ensures, his modification ensures, that you can charge this battery whilst everything is running, and even if you discharge the battery too low, so below 2.9 volts for example, you still end up charging the battery with the solar power, and it doesn't prevent the load of the circuit does not prevent the battery charging. I didn't want to go down that route, one because his modifications required, well, even he said some quite ugly hacks, and he wished the manufacturers had put those in, but I thought, well, I'm not really interested in running this off a USB supply or a solar cell, because once again that's a wire out of the bin lid, got to be mounted somewhere, and I don't like all these wires everywhere. So I thought, no, we'll just keep it on battery and charge the battery up every now and again. Fine. Okay, so that's one little section that does all that. But in conjunction with that, there's the, well, SI4599 down here, which is a dual MOSFET, and allows the power to be switched on and off via that tilt switch. And when it's off, it really is off, pretty much almost like a hard switch, you know, like your light switch. Yeah, and when it's on, it's on. Simple as that. Zero resistance. Well, all right. 0.0 something ohms resistance. So this is why I use it, because, you know, I did a bit of research, and the SI4599 works beautifully well, and indeed this replacement works as well. I can't remember what this is actually. Oh, there it is on screen. Look, there it is. That's the replacement I use for that. It's a plug-in replacement, drop-in replacement. Okay, fine. So those 3 things, that, and that, form basically the power side of this entire circuit. Let's see if I got that on the schematic. Right, this is my schematic that I've drawn up in EasyEDA, because I just like EasyEDA and I find it intuitive, it works well, lets me draw all this stuff out, and yeah, it's perfect. So let me just zoom in on that. There we are. Right, so we have the battery over here, and if you notice, the battery ground is not connected to the circuit ground, because the battery ground is controlled via the TP4056 charger over here. So the battery ground goes in here, there's the battery positive and output, but the out negative here is controlled by this. And if you really want to know a bit more about that, there's some links below, and as well as a link to Andreas Spiess's modifications of this to allow this to be used with a solar cell and not flatten the battery if the sun goes in for days on end. Fine, so that's the battery charger bit, and here's the battery. So what's all this? Well, all this here is to do with the SI459 auto switch on off bit, which we've covered many times in previous videos. Basically it's a dual MOSFET. Basically I've got a decoupling capacitor here, the resistor to keep the thing switched off unless we actually switch it on via this switch here, and then these diodes allow me to control and detect what's happening at that end via the microcontroller. And we went through that a little bit with the dual switch detection of my fridge door alarm. But here we only want one switch to be detected, so that's the lid state here from the Arduino, and this one here just allows the switch to be closed without affecting any other part of the circuit. Now I have got a 10 microfarad capacitor in parallel with that switch to stop any switch bounce and to allow a sort of slow on off. So really that's the power control module sort of finished, and you can build this on a workbench with a breadboard like I did, and make sure this works to your satisfaction. Just use a couple of DuPont cables for this just to make sure you can detect the voltage, and you go, that's one bit of the circuit now, I know it's working, it's been tested, great, let's move on. Now, of course, the most important part of this circuit would be the nRF24L01 talking to its counterpart over here. So what's that?
Tell us about the receiver unit.
No, we're not going to talk about this one. This is literally a dumb receiver. It's taken from the sketch of video 17, I believe. There, that one there, look. It's taken from that, plugged in here. I proved that this would talk to each other, as it should do. After all, nothing's changed over the last 4 or 5 years. But I've made this even dumber now, in that this doesn't send stuff back to here. Not yet, anyway. I'm thinking about doing that. It just says, yeah, I've received this, this, and this, and that's the end of it. The end. So we're not talking about this at all, because I'm not thinking about what I'm going to do with all this data coming into my workshop at all. That's a different project in itself, isn't it, really? I know I need certain bits of data to come in wirelessly, but what I do with that, whether I display it on a screen or show some LEDs or beep, don't want too many beepers, do we? That's for another day, not now. So we know this is an important part that's got to work, and it's just a plug-in module. If you notice, it's not plugged into the adapter plate because I've got my own voltage regulator for this over here. This is an MCP. Let me bring it nice and close. It's an MCP 1700. You can see down there. And it's got 2 capacitors as per the data sheet each side of it. And I think I've even got a decoupling capacitor here for this board, even though there's probably one on here. But I thought, well, while we're here, we might as well do it. And this capacitor here is a sort of reservoir capacitor for this, because this does sort of, give a sort of a burst transmission, doesn't it? A sudden burst of energy goes out, and I didn't want this sort of not being able to supply it. So there's I think this is 100 microfarads. Don't know if it's needed, but I thought, well, as I've got the space, I might as well do it. It's better to do it and then perhaps not fit the component, just leave it empty, than not have a space on the PCB and suddenly discovering you do need it. If you notice over here, look, there's space here for 3 components that I've not fitted because I don't need them and I don't intend to ever fit them. But if I had wanted to, I could. Okay, so that's the NRF with the voltage regulator. What does that look like on the schematic diagram? Right, so the wireless transmission module is down in this corner here. We'll just zoom in on that a little bit. There we are. So basically it's the module as it comes, from eBay, Banggood, wherever. There's a couple of resistors. There's a resistor here to make sure that I can switch the thing on and off remotely. A couple of decoupling capacitors. There's the 100 and there's the 100 nanofarad. As I say, the 100 nanofarad I probably don't need. It's just one of those things, belt and braces, because I'm not quite sure what's on here. I could have stuck it under the microscope and had a look, but whatever. Now, the whole point about this unit, of course, that it's probably one of the higher power consumption units. It takes about 10 to 13 milliamps while it's transmitting, and even 10 or so while it's doing nothing, just waiting for the next byte to transmit. So you don't want this on while we're waiting with the bin lid up. So by changing the CSN, chip select not, that stands for, basically bring it low and the chip switches off and consumes, I don't know, 0 point something of a milliamp. Not quite 0, but close enough. So that's the wireless transmission. Let's have a look where the voltage 3.3 volts comes from then. So here we have the voltage regulator, and as I say, I've checked to see which is a good low voltage dropout regulator, and I found the microchip MCP 1700 series is very good. The voltage that it needs in on pin 2 versus out only has to be 0.2 or less than 0.2 volts difference. So to get 3.3 I need a minimum of 3.5 out, but even better, if you put a voltage in here that's lower, say 3 volts, you still get 3 volts out. Somehow inside it just sort of shunts the voltage through, so that my transmitter, the nRF24, will continue to work even if that battery got really flat. And all it needs is 2 capacitors each side as per the data spec. So lesson learned there, always look at the data sheet just to see what the manufacturer recommends. And by recommends, it means if you don't do this, don't blame me if it all goes horribly wrong. So finally then we come to the actual Arduino itself. As I say, this is a DIP chip, DIP28. Yeah, if you notice, of course, all the components on here are through hole, because I figured, well, if anybody did want to make this as a sort of a newcomer to the Arduino world and possibly soldering world, the last thing they need is the added complexity of SMD soldering. Surface mount stuff is I find it now okay, not a problem. But I do know I did find it a problem when I first started, so I thought, well, let's keep this through hole, even though the board tends to be bigger as a result. But then again, I'm not too worried about the size. If I was really worried about the size, I would have had to have gone the SMD route. But anyway, this is the Arduino. These 1, 2, 3 capacitors are all decoupling capacitors as per the spec sheet again. Because remember, this is a bare naked chip. There's nothing else going on with this at all. That resistor and that switch is for the reset button, which frankly I don't really need a reset button, but I have them, so I'll put it in. The 10K I probably don't need either. There is a weak pull up inside, but it is weak. And I've read on forums and things that sometimes that 40 to 60K internal resistor might not be sufficient. So I thought, okay, let's just stick a 10K on there and be absolutely sure. As I say, it's better to have the space to do it than leave it blank. Right, let's have a look on the schematic, what that looks like. So it's this rather scary looking thing here because, and the reason it looks scary is because it's got lots of pins, hasn't it? 28 pins.
80 tiny 85.
What? 80 tiny 85, you say? Well, I probably could have done it with an 80 tiny 85, but I find I end up struggling for extra pins. And we'll just think about that in a minute, right? Future development and all that. And I thought, I've got these 80 mega 328p chips. Let's use them. Let's have a look at this bit then and see why it's not so scary after all. Yes, there are lots of pins, but look at this top few here. This is all the A0 to A5. Well, they're just going out to a header and doing nothing for future expansion. These here, D2, D3, D4. They're doing nothing. They're going out to a header as well. Then we've got the latch, which keeps the thing powered up. We've got the lid state, so I know whether the bin lid is open or not. That is also part of the nRF, and CSN is to shut it down if I want to. The speaker buzzer that you saw on there uses 2 pins, so we get the rather useful increase in volume by having the pins go alternatively high and low. No, it doesn't mean we get 6 volts or whatever it is out of it. No, we don't double the voltage, but the effect is as though we double the voltage. So that's a very useful thing to do, and I'm using the Tone AC library for that. And it always uses pins PB1 and PB2 because that's where timer 0 is attached to. Then we got the SPI pins here. That's used for the nRF as well. And round here we have 3 decoupling capacitors. You absolutely must use these. I don't think you can get away with not using them. They're only 100 NF, so they're pretty tiny. For both VCC, AVCC, that's the analog part of it. Now AREF, I decoupled with 100 NF as per the datasheet because I'm going to detect the voltage of the battery. And the way you do that is you compare that voltage with the AREF voltage, which is 1.1-ish. Okay, we've actually been through this in one of these. There are that video there. We've been through all that, and I'm making use of that here. And it's accurate to within 0.05 of a voltage, more than accurate for us. And that's pretty much about it, isn't it? Oh yes, the TX, as I said before, the TX always is brought out so I can debug this if I need to. And that's probably about all we need to talk about the microcontroller part. Yeah, there's lots of pins that aren't used, and it looks scarier than it is, but this is just a schematic component, isn't it, really? So we've talked about the power control module, the microcontroller, the battery charger, the voltage regulator for the nRF. There's the expansion pins I was telling you about, D2, D3 and so on. Always worth bringing them out. You never know quite what you might use them for. The programmer, yes, we didn't actually discuss that. That's because there's no USB socket and circuitry, CH340G or anything on this board. Why would you do that? You're not going to have a bootloader on here, are you? It'd be madness. You always need the 6-pin socket on here or plug so that you can update the code. Easy to do, and they go into these ones over here. If they're shared, as they are in this case, you have to make sure that whatever it is you're sharing the SPI with is not going to interfere. And I considered with the nRF either having some jumper wires on the board So I can unplug a little jumper to turn this absolutely off, or as it says, make sure the CSN is tied high, which I've got here in this little resistor here. So we've covered that as well, and there's just a picture of the dual MOSFET that I'm using up here to turn things on and off, and I'm not covering that anymore because we've done it so many times, but it is so useful. When you get one of these little things, you think that's the answer. That is the answer for my future designs. You might as well stick with it, and I will. Right, what's next? Well, the next step, of course, having spent quite a bit of time on the schematic diagram, and that's where your focus should lie, because that's the bit that has to be 100%. I then converted that to a PCB, as you see here. Now, this is all fun and all that, and yeah, the layout isn't critical. After all, we're not designing microwave anything. You know, even the radio frequency stuff is all self-contained here. So, you know, where the wires go and all that aren't too important. As you can see, some of the tracks on here are thicker than others, like this one here and that one there. So basically my power lines are thicker than the signal lines. They're all, I can't remember what I set them to now, basically as fat as I think they need to be. So that might be 20 mil or 25 mil or something like that. And the others are all something like 15 mil wide, whatever seems sensible at the time. So yeah, that's fine. And now EasyEDA not only allows you to create the schematic as you saw, that nice picture, it will convert it into a PCB. Yes, you have to put the components where you want them and where you think they're sensible, you know, these things on the edge of the board and whatnot. And then just hit the AutoRouter button. Yep, now, I know this is like throwing fuel on the fire. I mean, if you guys can argue for hours on end about whether you get a 6 volts on 2 pins coming out, you'll argue about this as well. But frankly, I've got no time with manual routing of tracks on a PCB. I let the AutoRouter do it 100% unless I think there's something dodgy going on. And the AutoRouter for EasyEDA has come on in leaps and bounds in the last few months. I used to have big problems with it. It used to say, no, can't do it, can't do it, can't do it, fall over. And you'd have to move components around and sort of cajole it into giving you something. These days, I can't make it go wrong. It just... And JLC PCB say, look, if you do find something it can't route, send us the circuit diagram because we'd like to know why. Don't forget to download the local router, otherwise you're competing with everybody else for resources on the main server, and quite often in busy times you'll get a little message saying server too busy, try again later, which is frustrating to say the least. So download the local router, which is available on EasyEDA's website, and you can do it as many times as you like, and it really does work well. I'm quite impressed, I've got to be honest. Right, so that creating this, and yeah, in some ways you'd almost expect to have a V2 version. But you don't go into it thinking, oh, well, this is just a rough and ready design. No, you hope to have the final design straight off, don't you? But sometimes you have to think, that didn't work too well. So what didn't work too well on here? What things would I have done differently? Well, there's a couple. If you notice, the nRF24 footprint, which I just took from the EasyEDA user contributed part, fits in there rather nicely. So I thought, oh, okay, that's good. And underneath, I know that I should remove the copper, so I did, from where the aerial is. And then, of course, when I plug the thing in, having not tested it and checked, I find it overhangs the board by quite some bit, doesn't it? Look, you know, there's a good, nearly a centimetre overhang in the board there. I thought, oh, didn't realise that. So yeah, that's something to test. And at the same time, if you notice on here, the ICSP socket that should be here is too close to the edge of that board. So if I was to have this vertical, I probably couldn't get the plug on it. So I thought, aha, I'll put right angle pins in, which I have. Yeah, it's a standard right angle pin. Except now, of course, it makes the board wider at that point. And remember, the board was designed to fit this case exactly. Luckily for me, and it is pure luck, nothing else, I can still squeeze this PCB in here with the pins. Look at that, it just fit. I can close all that up and that is a waterproof, well, environment proof case, and that works absolutely fine. Oh, I'll tell you, cack-handed, it doesn't even begin to describe it. Anyway, you'll see all that when the whole thing is finished. By whole thing, I mean this all up and running with minimum viable code in here, which I've sort of got, you know, the basics working, as you saw. What, you didn't see that? You didn't catch it? We'll come in onto it in a minute. But of course I've got to design some sort of receiver unit here and decide what I'm going to do there. Don't know what I'm going to do, frankly. Anyway, luckily for me, although that board is not perfect, although it's done perfectly by JLC PCB, they've done exactly what I've asked them to do, and I'm not going to have a version 2 of it. Let's have a look at the output then, if you missed that. Now, this squiggly stuff here on the output comes about because, as you can just about see there, it's gone to sleep. So it sent the data, gone to sleep, and whilst it's asleep for those 8 seconds, I've disconnected the power. Because this also, I notice, affects what happens over on here. Once we've got some rubbish output here, I don't know if this is half received something or not yet. All right, I haven't got that far. But if we now, I'll just tilt the board again. See, look, the receiver did not put anything out here, even though this said, yeah, it received it. It auto-acknowledged back, but that did not receive it. That time it did. So 11:15, 11:15, the second time it did it, but not the first time, and so on. It will do it from there on. Okay, we're going to leave it there. I hope I've shown you, well, newcomers especially to project design, how you can treat each bit separately as per that circuit diagram schematic that I showed you, and how you can break each bit of that down and make sure each bit of it works before you start designing any PCB. That comes later. And of course, yes, this is all nice and neat now and beautifully presented. But remember, this is all scribbled out on a piece of paper first, just to prove it works on a breadboard and things like that. Then you think, right, that is the design I'm now going to take a snapshot of and put it in here, because this determines what your PCB looks like. Okay, I'm sure you've got your own ideas about the way I should be approaching projects like this. And this is, I'd consider this a fairly simple project. There's not a lot going on in it. Okay, enough talk. Thanks for watching. Don't forget, please do give me a thumbs up. Do go and visit my sponsor. And yeah, like the video generally. Comments down below, please. See you in the next video.
I hope you're finding these videos useful and interesting. There are plenty more videos to choose, and a couple are shown below. And if you'd like to subscribe to this channel, just click on my picture below and enjoy the rest of the videos. Thanks for watching.